Steve Christmer has worked in the rail industry for 38 years in both passenger and freight railroading in the areas of track engineering, vehicle track interaction, and the wheel-rail interface. Steve was employed at the Association of American Railroads, or AR, Research and Test Department, LTK Engineering, and more recently at Amtrak until retirement. He has a Ph.D. in civil engineering from the University of Massachusetts and teaches part-time at the University of Delaware in the Railroad Engineering program. Steve is the past chairman of the ARIMA High-Speed Rail Committee, Committee 17, and is presently on the ARIMA Board of Directors. Please welcome Steve.
All right, John, thank you much. I'm going to now share my screen if I can do so. Presentation mode, and I'm hoping everybody is seeing that slide. Okay. All right. Well, folks, this is a last presentation, and it is a little bit daunting, especially because of the expertise in the field of economics that we have on the panel, which I'm so glad we have. At least I think I'm glad. Once my presentation is over, this is about free and open debate, and we all welcome that. So, yes, I do venture into a little bit of, sorry for the sirens in the background, they'll pass shortly. The subject of economics does creep into my presentation, and I trust that, when at the end of this presentation that people will weigh in and tell me, educate me, and that's certainly the goal of this entire webinar. All right, so folks, the title being Meeting Engineering Challenges of Mixed Freight and Mixed Passenger and Rail Freight. And as you'll see as I go through the presentation, we're going to be pulling a lot of examples of improvements that have happened as a result of a program that started about 40 years ago, moving toward heavy axle loads on the freight railroads. The roads were very aware of the problem that had happened some 10 years before that, where the industry was not ready for the increase in loading from 70-ton cars, that's capacity, to 100-ton capacity freight cars. Quite a significant upstep in loading, and the track simply was not up to the task. And some rather unfortunate results came from that. So with that fresh in their minds, when the car capacity increases from 100 tons up to 110 and 125 ton were about to come along, the freight industry wisely got ahead of that, put a lot of research money into improving material strength, improved maintenance techniques, better methods of analysis, and so on. And a lot of that came through AAR research and test. So I'm going to be describing some of those really successes that came out of that were applied, and we were able to get ahead of the problem such that we did not repeat any of the disastrous happenings that with going from 70 ton to 100 ton. Yeah, we met the challenge, and what I'm going to hopefully show is how those benefits can now be applied to maybe the next challenge that is facing railroading. So we are talking here about building on the success that I just mentioned regarding increasing freight car capacity, which we now can use some of those same tools and methods that came out of that study and effort to perhaps invest in increased track capacity for higher speed freight and higher speed passenger, regional, perhaps long distance as well. Now, why do this regarding the higher speed freight? Well, to capture the higher value, higher profit express freight. And there's one more higher that would go in there, that is higher speed, of course, too. Now, what are we talking about? This is somewhat lighter loads, maybe going back to the 70-ton cars, that sort of loading. And in terms of speed, well, we'll get into more detail about exactly what speed range we're talking about. But for now, let's just say more than 80 miles an hour, which conventional freight equipment has a hard time achieving in excess of 80 miles again, as I say, we can do this by building on the advancements that have already been made in track engineering to withstand heavy axle loading, or HAL. The question then might be, well, how do we expand track capacity? There's a number of different ways we could do that. We've already talked a little bit about that during this webinar. Of course, increased or improved signaling can have the effect of increasing speeds and track capacity. Better methods of maintenance that reduce your track occupancy of maintenance equipment, such that the track is then more available with better, more durable maintenance methods, and increase in track capacity. And if we even want to consider Gil Carmichael's suggestion of electrifying the locomotives, have electrical power powering the freight, then that, of course, too would increase track capacity, because your electric locomotives would have a faster rate of acceleration and deceleration. But I think for now, we'll just focus on expanding track capacity by the more conventional means, which means to build more track, or take an existing lower class track and turn it into a higher class track, which allows increased speed, of course. Now, there's this slide I was able to obtain from these three gentlemen that are mentioned there in an excellent paper that was just presented at ARIMA last month, and it very well frames what the three different modes of shared use rail corridors. Shared meaning between freight and passenger. We have on the left the shared track, which means that in this case both tracks are electrified. Therefore, if it's electrical locomotives for passenger service, they would have to go on either track. And then, therefore, the freight could go on either track as well. So either freight or passenger will share both tracks. An example of that is the Northeast Corridor, as I'll show in just a second. Then the next one, shared right of way, where maybe one track is dedicated to the passenger service, say higher speed passenger service that's electrified, and then the adjacent track is perhaps for the freight. Now, that's where you might have a class 6 track on the left, maybe a class 4 track on the right. And as long as those two don't mix too much, you're okay, maybe. I want to show the next slide before I go on to show what can happen with case number 1 there. As I say, that's our situation on certain segments of the Northeast Corridor that Amtrak maintains, where again, freight can be on either track, shared with the higher speed or high speed passenger service, which is class 6 or perhaps class 7. What happens here, as we have seen, and this is actual track, 2-track territory, high speed tracks, but it is shared with freight and heavy axle load freight at that, 110-ton cars. And over the years, you can see what has happened to the track deformation. You have a somewhat soft subgrade that has deformed due to the loading it's seen, such that there's now a soft subgrade depression and dip, which also can retain water and sort of had a progressive kind of movement, keep on moving, keep on shearing, because it's soft, of course, and deformable. And then if water is retained in there, nowhere for it to go, that further exacerbates the problem. Now, this is not a safety issue because that deformation rate is fairly slow, but it is a maintenance issue because it means that you're out there possibly a lot, very frequently, trying to tamp up that track for profile and maybe cross level as well, where as the subgrade shifts and shears, then ballast falls into that dip as it gets bigger. You have to come out with your maintenance facilities or equipment and tamp the track up. And if you're trying to maintain class 6, let's say, you're going to be tamping that track quite often. So again, not a safety issue, but it certainly could be a maintenance headache. Now, this is a feather in Amtrak's cap that, because I don't think, to my knowledge, no one else in the world tries to operate this situation with high-speed trains and loaded with heavy axle load loading. We do it, and I think we do it rather well. But is it an optimum choice? If you had another choice, would you make that one? Probably not. You might go with the one shown in the middle there, case 2, or possibly preferably, if you can, if you have the right of way width to accommodate it, option 3, which you then separate out the higher speed passenger and the higher speed freight as well. I showed to Acela power cars, but that could be higher regional higher speed passenger along with higher speed freight too, dedicated on those tracks. Whereas on the right hand side of that number 3 case, you have the standard freight and possibly heavy axle load freight as well over there. So class 4 perhaps track on the right, and maybe class 6 or higher on the left. Again, that's if you have the right of way width and the ability to build the extra track to accommodate that. And we could talk also about whether a barrier belongs there. There's a risk management tool that's referred to there. That is a paper I encourage you to read because that does address that issue, but we're not going to go into that detail for now. All right, so I want to take you through some of the things we did at Amtrak where we did add track and it helped enormously. And we'll start with some simple civil engineering cases, examples, and then we'll build up in terms of more complexity of how we can maybe provide this service, the one on the right. So obviously, if you have a single track main and you want to increase that to double track, that's going to help you quite a bit in terms of added capacity. So some of the things we had to weigh and consider are where is the right of way? We consult the real estate department and see, well, do we in fact have a room to add the second track, the one on the right, track 2, and allowing for considerations of, well, we had to have a roadway going out to some width there, and the drainage ditch beyond that, does that or does that not conflict with the existing right of way? Even more problematic potentially is the graph on the bottom where you have wetlands. It be in this case more restrictive where the wetlands barrier comes inside of the right of way. So you're not going to do much with the track on the left, track 1. But the track on the right, new track 2, is also a potential problem for us because here, sure enough, where the wetlands coincides with the right of way, we would be violating that or encroaching on the wetlands. So what we have to do in such cases is we have to look at some retaining structures, such as you see there, which if you didn't have that, then the slope would be in the red dash line, and that would encroach outside of the wetland. So permitting would be a problem. You might not be able to do it. Therefore, we do have the straightforward methods of going in and putting in a planning for a retaining structure to allow you to draw that the slope into the gray line, which does not exceed the property, the right of way, or the wetlands. Again, this is fairly standard, so nothing too fancy about that. We certainly understand how to do that, but it is part of the planning process and the costing that would go into, can we do this? Now that's fine for what the track looks like externally, but we want to know what is within what it says there, what lies beneath the track structure, within the track substructure, because that is such a key part of this. And again, what came out of all this investment over the recent decades, looking at how do we address issues of heavy axle load, how do we make the track ready for that? Well, one area of development has been the ground penetrating radar measurement system. Back when we were the industry was only just thinking about heavier axle loads going up from 110, this technology was sort of in its infancy. But over the decades, in large part because of the demands placed upon it to know what's going on with the track substructure, this was further developed. So what you're seeing is some transponders that are suspended off the back of that high rail vehicle. They are bouncing a signal into the track substructure and listening to the echo coming back, processing the signal, and then from that you can determine quite a bit, as we'll see just in a bit for a couple of examples. The typical case is what you see on the left, where it's on a high rail vehicle, you're looking into an existing track structure, but you may well want to look in at the case on the right where it's proposed that you have a new track placed over an existing road bed, and where you're going to double track a main line, let's say, that's where you would want to maybe, you know, there's no rails there, obviously, so you'd have to sort of slowly drag those GPR transponders across, but it's the same idea, and the output that you get out is you know, just as valuable. An example of a couple examples of what we find. Here's one where we're looking for the amount of deformed layers or deformation within the substructure layers. Now, why is that important? Well, let's say we have presently a track 1, but we don't have yet a track 2 that's proposed. That would be new track construction. You might want to go over this existing road bed because there was very likely a track there at some point back in its history. And if you just place a new track on top of it, you could reawaken instabilities that are latent, that are just in there and will be reawakened once you start loading it. You want to know that before you put track over it. Or it could be a case where track 2 is going to be upgraded. Perhaps it's a class 4, you want to make it a class 6, and it's the same issue. You don't want to be caught unawares of some instability that when you do increase the loading and you hope to maintain a nice track geometry, you want to be sure and remedy anything before it gets that far along. All right, so that's the hot spots that you're seeing there indicate more deformed subgrade surface. So that cross section AA is indicating that you're looking down on plan view at the top, and you're seeing the cooler colors indicating, well, nominal conditions, no problem. But where there's an excessive deformation, the GPR data can show you that in terms of the heat plots or the colors, red being more critical, hotter colors being more critical. So that is a case where you have a zone where it has been soft and deforming in the past, certainly could be or will be again, and this is telling you that might be something you want to address before you go any further. So that's a GPR measurement that can look down into the substructure by some depth. You could also look more shallow depth. If my cursor works here. So that's looking down here in this case, but you could also tune it to look sort of at a more shallow depth, let's say in the ballast, to look for how much ballast fouling there is in an existing track. An example shown here. Here you have, looking down from above in a plan view, a 4-track territory, and you can see by the heat plot again, hotter colors mean more ballast fouling. Drainage is, the ballast is poor in those areas, something that you might need to address. Again, if track 3 is the existing track you're looking at to upgrade from perhaps class track, FRA class 4 to class 6, you might well want to know those areas so you can address them, remove the ballast, renew it, or whatever you have to do to improve the internal drainage before, to improve before the class 6 service begins. So all techniques that are now available that can lend themselves also to increasing speed as well as increasing the loading as has been done. Another thing that is vitally important is to not have to maintain your track so often such that your maintenance equipment gets in the way of your revenue trains, of course. Those spots that show as heavily fouled, they're probably maybe joints or something that causes a lot of dynamic load. And then because they deform, you have to come in and tamp them. Well, the tamping itself also degrades the ballast, right? So it's a further whammy against having good conditions. So what you would like to do, be able to do, is have better maintenance methods that don't degrade the ballast as much and also give you longer lasting geometry corrections. There are a couple that have been developed over the years, again, with the intent to address the problem of increasing axle loads to make it a more durable track. This is a type of maintenance known as stone blowing. It was actually developed in the UK, and we brought it over to the United States. The process is one where instead of tamping the track, you would use a different system. It could be handheld tools, or there is a mechanized version of stone blower too. But the process is one where you would raise the track as shown from 1 to 2. At 3, it shows an ejector tube being placed at a certain depth so that you can blow stone underneath the tie. That's where you You see that in number 4 there. So air is introduced. That's a venturi tube. There's an orifice that restricts the flow, and then on the other side of the orifice, where it suddenly opens up, that makes the ballast pick up speed and shoot under the tie as shown. And then case 5 shows where you place the measured amount of stone, and then you lower the rail there of the tie onto the stone-blown material. This whole process is minimally disturbing to the ballast. It does not degrade the ballast hardly at all, as tamping does, and it also does not loosen the ballast. Therefore, you're building off a stable base. That's where the increased durability comes from. And how much more durable than conventional tamping? It could be typically 3 or 4, but we have seen 5 times and more increase in durability over conventional tamping. Again, something that lends itself to especially the higher track classes, where you're kind of going in and you're just sort of feathering in a geometry correction. So maybe on the order of an inch or less. That tends to be upper classes, class 6 and so on. So it lends itself more to the higher speed service, higher speed freight, higher speed passenger as well. Another technique that also has been developed to address this very issue, to get an increased durability of maintenance, is uses a tamper in this case, but in a different and innovative way. It's called design overlift tamping. And the whole approach here is to take your existing rough track profile, which is the bottom line here, right? And raise it to a certain level, but then overlift it beyond which it would be level where the dip is removed. You actually raise it above the amount of the dip, so that once it's up there, what you can count on, you know this is going to happen. When you tamp track, you get an initial fairly large settlement. But what you don't want to do is bring the track up to level and then have it settle back substantially, maybe all the way back to where it was. You want to account for that initial settlement that happens with the first few trains by overlifting it by a design amount, such that when traffic begins to pass over, it settles back down rather fast initially, and then slower and slower and slower, so that it spends a lot of time right at that design elevation shown right there. So you're accounting for the mechanistic or the mechanism of ballast settlement, and you are raising, depending upon where you are in the dip, a measured amount so that you end up with this optimal smooth profile. And this has been shown to work, as has stone blowing, for heavy axle loads, for high-speed trains. It works really everywhere. Here's an example of how well this works in the case of design overlift. Here you see your original rough profile rail, and then immediately after you've designed overlift. So it's not optimum. It's a little bit rough in the other sense. It's a little bit raised up. Not too bad, but it isn't perfect. But it does approach the design after some traffic. You see how after 16 weeks it settles quite a bit, and then after a year it's pretty much settled into what you might call a smooth design, and then degradation thereafter is slower and slower. So it never really returns to where it was. That's a problem that often happens unless you apply some improved techniques such as this. So basically you're kind of removing ballast memory. This can be done. And once again, the improvement of design overlift is about the same over conventional tamping as stone blowing does. It's about a factor of 3 or 4, lasting longer than conventional tamping. So you're out there maintaining it less. You're also degrading the ballast less. Medical professionals say, first do no harm, but we as engineers, at least we can say we want to reduce the harm we do. That's the goal of this. All right, well, we haven't talked about what speeds we're referring to when we say, not yet anyway, about higher speed freight or higher speed passenger. I want to talk about that in the context of the FRA chart on the left, where it's the limiting amount of vertical deviations or dips in the track over some chord length, 62 feet in this case, based on FRA track class. And then the table on the right, which relates the track class to the allowable maximum speed for both freight and passenger. So if I go to the next slide, we'll see what speed we're talking about in this case. Typical for freight, you might say, is a class 4. And you can see the speeds that are related to that. So for higher speed passenger, how fast are we talking about? Well, let's first make it easy. Higher speed passenger for class 6 is 110, and totally achievable, of course. But what speed are we talking about for higher speed freight? Now again, when we started this, we said, well, something greater than 80 miles an hour, which the conventional 3-piece truck has a hard time doing. So we want an advanced truck that can, so we compete with over-the-road trucks, something greater than, well, let's see, 80 miles an hour, certainly. Maybe not as fast as 110, although that's something that could be attempted. But here's the issue. So as I said, the conventional 3-piece truck often has a problem trying to pass the stability requirements as you approach 80 miles an hour and get beyond it. Now, typically, the 3-piece truck has no problem getting up to around 70 miles an hour, and you may get a little bit more. But there's that barrier at around 80 miles an hour where, although the 3-piece truck is robust and very forgiving, a real workhorse for the industry, but we're simply asking too much of it as we get above speeds or higher speed freight above 80 miles an hour. So what we want to do is, if we want to compete with over-the-road trucks, we have to have an average speed of around, let's say, 60 miles an hour. And I think Dennis Newman mentioned 60 miles an hour being the target speed for the higher speed passenger, as well as for an average speed. Well, to get that as an average speed, we need to have somewhat of a higher maximum speed. So now we're getting a little bit better defined in terms of what we're talking about. To get around 60 miles an hour average, we might have to have a maximum of, let's say, at a range of 90 to 110 miles an hour, which requires class 6 track, which again goes back to the same for the higher speed passenger service as well. So we're talking about roughly the same range of speed for high speed passenger and high speed freight. And beyond that, the wheel loads are about the same as well. So that all helps to keep, it's in the same sweet spot or footprint, if you will, for both of those. So that, they don't get in each other's way. One does not cause an excess amount of degradation to the track than the other. So they kind of complement each other as long as they're kept separate from the higher speed, the heavy axle loads. And nobody gets out of my class at University of Delaware without being able to use analytical methods to show just how much track deformation comes from heavy axle load traffic compared to, let's say, a more lightly loaded passenger vehicle with different wheel loads, different speeds, and different unsprung masses, but we won't need to get into that right now. But all this can be accounted for. And a lot of this came out of, as I say, the research effort that stemmed from having to account for how do we deal with the coming heavy axle loads, which we now can sort of redirect and apply to higher speed freight. So that if we're talking about, what did we say again, 90 to 110 miles an hour, perhaps, for higher speed freight, we're clearly not talking about a 3-piece truck anymore. We are talking about something that's more advanced. Here's an example of one, a prototype that, well, it's more than a prototype. This has actually been tested out of TTCI Pueblo, and I think this report just came out earlier this year. So they are well into their validation phase for this. I think the upper speed it had attained was something over 110. The locomotive couldn't get above that, so they could have maybe gone higher and still stayed within the requirements, but that's as fast as they could go. But that's the sort of type of leap we need to make, and there may be European type trucks that can do this as well. But here's something that my former colleagues at AAR Research and Test have been working on. And as I say, this is pretty far along. But that's the sort of investment that would have to be made. Now, one of the aspects of concern of this, well, let me go back to the 3-piece truck. when I say stability, that this often, it may fail in stability, I'm talking about hunting behavior. And if you're not familiar, it's the lateral instability that can occur when the truck gets up to a certain speed and there's some lateral perturbations that excite the truck laterally, and perhaps and all of a sudden it starts to go into a hunting mode, which means lateral oscillations that do not damp out. That is safety critical, so it's obviously something we want to pay very much attention to. It's the stability problems of the three-piece truck start popping up maybe around high 70 miles an hour into the low 80s, but you can have, within improved design, a high-speed freight truck that can go well above that. And I should add this, so again, this gets back to, this is a fairly lightly loaded, you're sort of returning to lighter loaded, going back to 70-ton, which is appropriate for the level of service that you might think of initially, lighter packages, parcels, maybe, but that needs to be expedited. Perishable produce from the San Joaquin Valley, let's say, coming out of California and going to points east, that sort of higher speed freight. That's time sensitive. And when we talk about stability, we're often, well, there's a number of things that contribute to, is a rail vehicle stable or not? But the wheel-rail contact, and especially something called the equivalent kineticity, is something that is vital to watch. And here's where, again, I say much research has gone into this sort of wheel-rail interface. And we can take from that the benefit of that research and result and apply it to higher speed freight, just as we already do to higher speed passenger. Now, when I was at Amtrak, we were well along in developing this, because obviously it's safety critical for high speed passenger, as a way to monitor your wheel and rail profile, so that as they both degrade, the equivalent kineticity, that is to say the kineticity that's at the point of contact, right? Not just the tread taper, but rather the kineticity that results from the mating surface of the wheel and the rail, where those red dots are that you see there. This is an example of a vehicle in a curve, so you have flanging on the right-hand side, and so the contact point is shifted into the flange throat, and that's a natural condition for the equivalent kineticity to be somewhat high. Now that's in a curve. We're not so concerned about stability in a curve, but when that contact happens in a straight, in a tangent, that's when you do have to be concerned about possibly the equivalent kineticity getting too high and instability happening. But as I say, this is something we've thrown a lot of research at. We understand that. We have the analytical models available to see when that's coming. We can predict it well in advance. We monitor the degrading profile of the wheels and the rails, and we can say, okay, the equivalent kineticity is starting to increase. At some point, it's going to get to a threshold where we say, okay, let's get that car to the shop and read through the wheels, or maybe go out and grind the rail, regrind the rail, to return it to a new condition and lowering the equivalent kineticity. All things that came out of the research effort over the many recent decades that can be applied now. Now, why do all this? And I say this advisedly because I understand we've talked about debt a little bit, and who pays for things and all that. Those are very good questions, and ripe for debate. But why necessarily look at any of this? Well, why do we need to change and to adapt to changing markets? I would just mention two things that come out of environmental concerns. The Union of Concerned Scientists provides the quote shown there, where net zero carbon emissions are the target by 2050 or sooner, and even sooner than that. The Intergovernmental Panel on Climate Change has set a target of 45% reduction in global emissions in just 10 years. Now, draw your own conclusions about how that changes what the freight railroads haul. But I think we as engineers have to sort of anticipate this, and as business people and anybody that wants to see a future, a strong future for the railroads, however we feel about this, certain changes are coming. They've already happened, and more are going to come. So here's where we tell the rail industry and the advantages that it already has: an inherently higher fuel efficiency. It starts out fairly green. It has a low rolling friction at the wheel-rail interface, the contact, and we can build on those things to make for a mode shift from passengers and goods from roads to the rail. So that, I have to check my time here. Okay, we're doing all right. So again, this could be seen as the why we might need to do something. I'm going to end with a quote that you've probably heard of before. I like it. Make those small plans. That's especially appropriate maybe because Daniel Burnham is the architect of the Amtrak station in Washington, D.C. And my final slide, which I can't see because something is in the way. We all have people, a lot of us in the industry have grandfathers, great-grandfathers in the rail industry. And so that's very common. But I bring it up only to say that they have given us a great inheritance of a strong, vital industry that we want to be sure and hand off to future generations, and so that we have growth that's stable and continued. As markets change, and maybe we can anticipate some of these changes and put the railroads in a good position to take advantage of them, not just survive, but in fact thrive. So with that, I conclude my presentation, and I look forward to any questions, comments, criticisms. It's all welcome. Let me stop sharing.
Well, more of a comment, though. I have to say, great presentation, Steve. It did start my thinking on several paths for research from things that you were saying there and had mentioned. So I'll have to continue with those and get you involved on that. But really, there's some great things to think about there. And with the technology advancing, the products can be changing. I just have to comment and say, very good. Jim, do you have any questions?
Yeah, but I wanted to make sure Steve got a chance to go first. Steve Ditmeyer, if he wanted to. I don't want to monopolize the questions. But so I have an observation. We did a cost-benefit analysis, Pradeep Patel and I, for Dr. Zaremski and Harsco Rail on their snowblower. And yes, we were able to demonstrate there was a business case that said it was much more cost efficient on a maintenance away budget if you use stone blowers for high speed or heavy axle load railroads than using tamping machines. Because one thing the tamper does is it basically starts to destroy the structure of the, from physical force, the stone, which then has to be replaced earlier. But we found that one interesting thing is Harsco Rail, this is off the record, I don't want to beat up on a company, but Harsco Rail is the only manufacturer that I know of that's got a license for the stone blower at a big scale. Never wanted to risk the R&D cost of building a machine and bringing it over here and using it as a demo. And so we never sold any stone blowers in North America, only in Europe.
Yes, Jim, I kept going after Harsco to say, please let us have a trial machine. They just never.
Risk adverse. It was a financial decision. On my estimation was a financial. Others may argue otherwise. So innovation was stopped because you couldn't get the manufacturer to take a risk, and no Amtrak or no North American railroad wanted to buy the machines. And interestingly, the converse was true for Conrail. Conrail, in its rush to rehabilitate the railroads back in 1976 to 1979, we bought European high technology plaster tamper machines and brought them over here. We were desperate, so we were willing to take the financial risk. Big difference. But this gets me to the other question. You need to, I need to connect you with David Burns. He writes for International Railway Gazette. He does a lot of work in China and so forth. He's moved from Chicago. He's now in Vermont, but I have his contact info. He did a study for a private client, and he never revealed the client, but I got to see his results. And it was for high-speed commodities that could use, he was using 90 to 100 miles an hour and wasn't going up to 110. And nobody bought into the study. Nobody could see that there was enough customer critical mass. You had to have enough customers on enough strategic lanes, and then the lane had to be contiguous from the West Coast to the East Coast. You had to have that two connecting Class 1 railroads that aren't merged, that are partners, that agreed to do the same, the preparation of the right of way, and then go into the equipment. Nobody would take the risk that we needed to go anywhere near that fast. So while the engineers like you can demonstrate the capability is there to build it, nobody's sure that you can actually make a profit. Now, I've been doing some work for a client, overseas client, which I can't divulge, and it had to do with battery technology, full-size battery technology, not this 2 megawatt hour battery shunter locomotive that Wabtec has. Something in the 6 megawatt hours, and then ways to charge it repeatedly to keep it running. And what we found is, if you go into a beta test like this, because that truck that you have in the first set of tracks, we're talking about a beta test project. Well, somebody like Tesla, Elon Musk, and billions of dollars is willing to throw money at that. Our industry isn't willing to throw the R&D money at that for a demonstration in the market at the prototype, or what I call the beta test version, not the full-scale long-term production model that's coming off of manufacturing lines. Now I'm talking about something that's the first test, and then you get into the first prototype testing manufacturing, which might take you, according to some of the engineers I've been working, it could take you 5 years worth of testing with a fleet of X number of vehicles before you get the reliability down to where this thing is going to perform. There's something wrong with the technology or the design or the manufacturing that's going to cause it to break and be more expensive and not give you the benefit you want. So you could be talking about 8 years to roll this out. And I'm not sure our industry is ready to do that. You got to find a customer that's willing to buy into this. And we're not even, we just talked about the failure of Union Pacific with this $300,000 unit car for the reefers, not being able to figure out how to keep it running, and then, so they've at least temporarily given up on the model. And we're talking about going into something that has an even higher financial risk profile. So the question isn't the great engineering capability that you have to test it. The question is, how do we commercialize it? Those are my observations, and I don't have an answer for that. And I don't want to discourage you. I just want to say, you got to get buy-in. You're not going to make a profit on this deal. So to go back to the battery test, the issue was, if we went ahead with the original test project for this one particular client, it would be a failure if 5 to 8 years from now we ended up that, no, their cost per delivered ton went up by X%, and now from being number 1 in the market, they're going to be number 3 as the supplier source. That's a failure, even though they had a great, wonderful, successful, environmentally achieved zero energy solution. If they go out of business, that's a bad business case. So this is really difficult challenge ahead, which
much the same, Jim. And I know you and Stephen and others remember improved steering trucks, freight trucks, right? And that, as you know, that foundered on the question. Well, yeah, I can see how they would lower wear and improve, but who pays for the benefit? They could never decide who was the appropriate part.
Whose pocket does the benefit go in?
Yeah, that's right.
And in the heavy axle case in England, when Alan Zaremski and I and Randy Weiser and I were over in England, we tried to convince them to get rid of the opposing joints and the single axle on each end of the car, and go to heavier axles, get their axle loads up to 28 metric tons at least, if get out of the 23 to 25 max range. But the problem was, because you have a separate owner of the infrastructure and a separate group who runs the trains, certain people ended up with the costs.
Yeah, that's right.
And they never figured out how to get the savings benefit, their share of the savings benefits, out of the pockets of the people who had fewer train starts and better utilization of the car sets into the pocket of the infrastructure company. So the model collapsed because you couldn't figure out how to do the deal.
Yeah. So engineers are going to innovate, but that doesn't necessarily mean that, yeah, I got you.
But somebody figures that model out. One of the young people that's in our class comes up with a bingo idea, or comes up with a way, for the intermodal to have get the production costs for this rapid load semi-trailer, so the trailer and flat car can have the same kind of almost equivalent cost benefits per mile that a double stack container has, so that we don't have to ship people out of semi-trailers, which are still rule the highways. But you got to get the manufacturing cost down from $300,000 to $100,000 level. Which engineer is going to come up with that magic formula, that design? There's the opportunity. And that would create growth, wouldn't it?
Yes.
So again, I didn't mean to discourage you from your R&D. I just want to figure out how do we demo this as a business case test.
Well, and it's always hit and miss, because now it was a striking success what we came up with for heavy axle load, because that had a niche that it fell right into, and the railroad industry said, yes, great, thank you.
Vertically integrated, so they didn't have to worry about whose pocket.
Right.
Because it was a vertically integrated company.
Yeah. I get it. No, I understand.
Bingo.
Yeah.
Anyways, I found your talk interesting. And again, I want to encourage research. Like, we don't do anywhere near enough R&D. I mean, we should be spending 0.5% of our revenues for the industry on R&D, or at least 1%, if we want to have a chance at growth, right? To support projects like yours. We don't spend anywhere near that as an industry. We're in a milk the cow situation, and we're doing pretty good at that.
Well, we're doing well now.
Now, yes,
now. Jim, your projections, I don't know. So,
well, I'm in my 77th year. I don't have to worry. But I'd like the industry to be successful. Absolutely. Steve Ditmeyer hasn't said a word.
I don't need to, because I agree with what's been said.
Oh, okay.
I've just been sitting here reviewing so many projects in my career and so on, where this separation of where the costs occur and where the benefits accrue, and how to resolve that it is a real life issue.
Yes.
And
the young people here don't know about that. So this is maybe their first introduction or little discussion.
Well, and also too, heavy axle loads were a complication within the railroad companies and within the railroad industry. Why? Because the civil engineers all knew that heavy axle loads were going to damage their track, and that they were not going to be able to get the budget to repair their track.
Right.
And it took some work on my old railroad, on BN, with the help of Zetatech, to convince management that the company would be better off for adopting heavy axle loads. But we pointed to the chief engineer, Bill Glavin, then, and said, but you cannot cut his budget.
You give him more money.
Increase his budget so that in transportation, we can save money. And I also recall one other person in the railroad research community who was complaining. He said, on my railroad, oh, we have to figure out how to make heavy axle loads just behave the same as the lighter ones. And I said, well, no, they do wear more, and you have to pay. He said, but my management doesn't understand. I said, you have to tell your management. He said, but they don't listen to me.
You have to present a business case and you convince the chief financial officer this is a good deal.
Yeah, and you have, and you have to be able though to get all of these people sitting at the same table. I know at the AAR research department that George Way, who was a civil engineer, was strongly opposed to heavy axle loads for that very reason. And it took some convincing of him. And again, the Zeta Tech analysis began arguing, and finally it did occur.
So don't give up, Steve, and to the young men and women who are students, the lesson learned from these old folks here, you have to figure out how to present a business case. Otherwise, your great idea will sit on a bookshelf.